Let us solve the question number 19 that is given in the question bank of data structure. The question is as follows. A set of functional dependencies for the relationship R containing the attributes A, B, C, D, E, F is given, and we are supposed to find the minimum cover for this set of functional dependencies. So minimal cover or canonical cover, what is it? So canonical cover is nothing but it is a simplified and irreducible set of functional dependency that is equivalent to the original set. In other words, a set of functional dependencies are given to you. Now, it may be possible for you to eliminate a few of the dependencies or maybe fine tune few of the dependencies, but still you can maintain the same equivalent relationship. If that is possible, then we say that the reduced set of functional dependency in which some dependency or some relationships are being modified or some relationships are being dropped, that reduced set is, if it is equivalent to the original set, then we say that that is the minimal cover, or that is the minimum number of functional dependencies that are required to achieve the same result. So now, as usual, how to solve this particular problem? First of all, let us write all the functional dependency. This is what you are supposed to do whenever you get the question on functional dependency or normalization, anything. First, write down all the functional dependencies. So I have written all the functional dependencies one after the other, and you notice that there are 8 functional dependencies or FDs that are given to you. And what is the first thing? First, look at the right hand side of the functional dependencies. And you notice that there are a few situations wherein you have on the right hand side, you have two attributes. You have to decompose them and make them as single attributes. So let's go and let us do that thing. So the first thing that we are going to do is we are going to decompose the right hand side of the functional dependencies. So we have two functional dependencies here that have two attributes in the right hand side. So let's go ahead and let's do that. So the end result is we must ensure that there is only one attribute on the right hand side. So let us start with the first one, that is EC equal to FA. From the EC equal to FA, we can say that EC derives F and EC derives A separately. So we are going to decompose this relationship. EC derives FA. We are going to say that EC derives F and EC derives A separately. Similarly, let us try to decompose the second relationship, that is CF gives B and D, and let us write that one. So we are going to say that from CF gives BD, we are going to say that CF gives B and CF gives D. Now with that done, we are going to, so we have decomposed one into two parts and the other one into two parts. So there are two extra functional dependencies. So let us write down all the functional dependency now. Now you will notice that on the right hand side, all the functional dependency of that you have written, the right hand side of all of them have only single attribute. So you notice that there is only single attribute on the right hand side. Now let's concentrate on the left hand side here for the functional dependencies. And you notice that some of them have two attributes or two or three attributes. So is it possible for us to eliminate any one of them and still maintain the relationship? So let us try to do that thing. So our next challenge will be to remove the extraneous attributes from the left hand side. So what we are supposed to do is check if any of the attribute on the left hand side can be removed without changing the closure of the functional dependencies. So let us start with the first one. And what is the first one that we have here is AB derives C. So let's take that thing and let us try to find out whether A alone can derive C or B alone can derive C. So suppose if A alone can derive C, then we can remove B and say that in this relationship, AB derives C, B is extraneous and it is not required. So suppose if it is doing it. So let's find out whether it is really doing that. So let's start with AB derives C. From A, let us find the find the closure of A separately, and let us find the closure of B separately. So when we try to find the closure of A separately, from A we can derive A itself. Now what I've done is I put it in the next this set. Otherwise I have to scroll up and down every time. So what I've done is I copied this and placed on the other a Word document here. So this is the same thing. Whatever which is here, that is the same thing I copied so that it is easier for me to give the explanation. So what we notice that from A you can derive A, and you notice that there is no single A in any one of them. So from A you cannot derive anything. But even if you are able to derive anything, we are not interested in everything. We are only interested in whether from A for this relationship, whether from A can we derive C. You notice that from A you can derive A itself, but you cannot derive anything. So you cannot remove this A from this functional dependency. Let us try to find whether from B can we derive C. So from B, you know very well, you can derive B itself. From B it is self, you can derive itself. What about the other? You notice that from D, if you notice anywhere from D, from B, you cannot derive anything. So from B also, you cannot derive anything. In particular, we cannot derive C. So both AB is required in order to find C. So in this relationship, you cannot eliminate either A or B because both of them will decide the C. Now let's go to the this relationship, that is BC derives D. So let's look at BC derives D. Let us find the closure of our intention is see in this relationship when we have this BC derives D, our intention is to check whether B alone can derive D or C alone can derive D. If that is the case, the other one, if B is deriving D, then C is extraneous. It is not really required. And in the same way, if C happens to derive D, then we can say that B is extraneous and it is not required. But let us try to find out before we venture into that. So we try to find the closure of B. We know very well from B you can derive only B. We cannot derive anything else. In particular, we are interested in knowing whether B can derive D, which is not possible. So B cannot be eliminated. Let us try to find with the C, can we derive anything? So from C, you can get C itself. Also, you will notice that from C, you can derive A. So from C, you can derive C as well as A. But both of them, we are not interested in that. What we are interested in is whether C can single-handed derive D, which is not possible. So we will say that both B and C together alone, they cannot derive D. So they both of them are required to get the value of D. So we will say that both of them cannot be removed. Let us go to the next one. In this next one, we have ACD will derive B. So let's look at whether ACD we can eliminate any one of them. So let's start with the see in this time our intention is to get whether suppose say if you are not interested in D, whether AC can derive B or whether AD can derive B or whether CD can derive B. Can we eliminate any one of them? So this is our idea. So we know very well that from A we cannot derive anything. From B we cannot. From C we can derive anything. From D also, if you notice over here, D can derive E, but D cannot derive B, so it is not possible. So let us try to find out whether AC can derive something. So let's try to find the closure of AC. From AC, you can derive A, you can derive C. From C, you can derive A, but A is already there, so we will not rewrite it. So we say that this is not going to work. So AC is required. Let us try to find whether AD can derive B. From AD, you can get A, you can get D. From D, if you notice here, from D, you can get E. So you get E. Nothing else can be derived. In particular, we are interested in B. B cannot be derived from AD. Now let's go with the CD. What will happen with the CD? From CD, you can derive C, you can derive C, you can derive D. From C, you can derive A. So we know that. And from D, you can derive E. So you write that thing. But all of them are not required. What is required for this functional dependency is two of them should decide, if at all you want to eliminate it, they must somehow decide B, but none of them, any combination AC, AD or BC, any combination cannot determine B. So we will say that we will not eliminate any of these attribute. Let's go with this one. BE derives C. So let's start with the BE. So we will start with B. We know very well B will derive B itself. It cannot derive anything else. So you cannot eliminate E. Let's look at E. E will derive E itself. And you notice that there is nothing, there is no single E here on the left hand side. So E cannot derive anything else except itself. So we will say that both B and E are required in order to decide C. So none of them can be removed. Let's go with the EC, whether it will derive EF. So let's start with the E. We know very well E cannot derive anything. Let's look at C, whether C can derive EF. C will derive C itself. Also, you notice that C can derive A, but what we are interested in is F, which is not decided by C. We will say that we cannot eliminate any of them. Let's go with the EC, whether it derives EF. So let's start with this one. EC derives A, not F. So let's start with this one. So let's start with the E. You know very well E can derive itself. So E cannot derive A. Let's start with the C. C can derive C itself as well as C can derive A. Now you notice that there is this attribute C that itself can derive A. That means E is extraneous. So E is not really required in this functional dependency. So what we will do is we will eliminate this E from the relationship, and we are going to say that this is the reduced relationship wherein C can only derive A. Let's look at whether CF will derive B. We know that C can derive C itself as well as A. So A from C derives A here. It cannot decide B, so it is ruled out. F, we know very well, F can decide itself. So it cannot derive something else. So both C and F are required, so we cannot eliminate any one of them. Let's look at this relationship. What is this relationship? That is CF derives D. Okay. So CF derives D. Let us look at this one. From C, you can derive A and C, but D is not decided. From F, if you notice, F cannot derive anything else. So both C and F are required in the decision. Now you will notice that we have this E derives E. Okay, I mean D derives E. Okay, we will say that from D derives E. We will say that no attributes are required because D derives E is required. So even if you last go with that thing, let's go with the last one. And the last one is now when we try to do it, you notice that C derives A. We have it is already given, and here after reduction, where is it gone? I think after reduction, when we reduced this EC derives A, we eliminated E, and we got this relationship. It was already there, and we got the same relationship. This is redundant, so we will remove one. We will keep only one of them. We will not repeat them. So we will not repeat them. So we will just keep a C equal to A in this relationship. So the final relationship will be AB derives C, C derives A, BC derives D, ACD derives B, BE derives C, and EC derives F. B can be derived by CF, D can be derived by CF, and E can be derived by D. So these are the set which are irreducible and which have only one attribute on the right hand side, and the left hand side cannot be reduced, and there is no redundant one which is available. I think this should have been one, but anyway, that is Microsoft Word has continued the. Let me make it this one. Sorry about that. So that Microsoft Word. So 9 relationship, it actually continued from here, that bulleted. So in any, that is a minor problem. Okay, so this is the set of 9 functional dependencies which are minimal, and that is why we say that this is the minimal cover of the given functional set. That's all. Thank you for watching. We will meet again in the other exercise.